Hello, in this video I'm going to be doing the exam 3 review questions, and we're just going to go through them one by one. So let's start with question number 1. Alrighty, a gas in a closed cylinder undergoes a particular chemical reaction. It doesn't tell you the reaction, so you don't need to know it. But it does say that it releases 79 kilojoules of heat to its surroundings and does 18 kilojoules of work. Alrighty, so the wording here is important. It says it's releasing 79 kilojoules of heat. So you have to kind of read it really closely. And it says doing 18 kilojoules of work. And this is a topic that was discussed in the thermochemistry videos, I think probably in the first one, if I had to guess. But anyhow, when you have a release of heat, by the way, heat obviously is going to be what we refer to as little q, work is little w. When you have a release of heat, that means the heat is coming out of the reaction, being produced by the reaction, and that is an output of heat. So that's going to be a negative value. So even though it doesn't say negative right there, you have to interpret it like that Q is equal to negative 79 kilojoules. Essentially, that's what that's saying. And then if the system or the reaction is doing work, once again, when a system is doing work, that's also a negative value, as opposed to having work being done on the system, which would have been positive. But this is a negative value because the system is doing work. So negative 18 kilojoules would be what the value is for W. So this is all about the signs, making sure that you're interpreting the wording as the correct sign. And then the follow-up sentence there is calculate the change in its internal energy. Remember, internal energy in chemistry is what we mean when we use capital E. That's internal energy. And change in just means delta. Change in internal energy. And the key here is that you just recall this very simple equation. Delta E equals Q plus W. And here, and if you remember when I was going over this equation, I said you're going to make sure it's all about the signs. This is what I'm talking about. Make sure you get the signs right from the wording. All right, and then you just put in your values. Now, these are both kilojoules. You have to be careful. If one of them is a joule and one of them is a kilojoule, you're going to have to make the two match in order to add them together. And you can just, you know, it doesn't really matter which one you pick. Just pick one of them and make the two units match. But these ones already do match. So Q, negative 79 kilojoules plus negative 18 kilojoules. See, I just always keep it as Q plus W, and I literally put in the Q for that one and the W for that one. And if you go to your calculator, when I enter this, I would literally just do negative 79 plus a negative 18. I mean, I know that this becomes a minus, but, you know, why not use the calculator? So then it becomes negative 97 kilojoules would be the right answer. All right, and that's how you do number 1. So now let's go on to question number 2. Question number 2 says, calculate the energy of a photon of light with a wavelength of 900 nanometers. Okay, calculate the energy of a photon of light is always the same equation. If that's all you're trying to do is just calculate the energy of a photon of light, the first equation I would write down is this one. The energy of a photon is equal to Planck's constant times frequency. All right, so notice in the question, it gives us the value of Planck's constant, 6.626. It's a constant, so it's a number that never changes, times 10 to the negative 34th joules times seconds. And then the other thing that the question gives us is a wavelength. Okay, the wavelength, it's telling us, be careful that wavelength is this letter, the Greek letter lambda. A wavelength is 900 nanometers. So what you don't want to do is accidentally put that in for frequency. It is not frequency, it's wavelength. However, anytime you are given wavelength, you can get frequency, because obviously you see that's the number that we need. We have this, we need that. So that's going to go in here in just a minute as soon as we can find it. Wavelength will allow you to get frequency through this equation. The speed of light is equal to wavelength times frequency. So we need frequency. Let's go ahead and solve for frequency. Frequency is going to equal speed of light over wavelength. The speed of light is always the same value, 3.00 times 10 to the 8th meters per second. I wouldn't give you that in the question because I expect you to just have that memorized. But divided by the wavelength. Now the wavelength, you can see the length unit is in meters in the speed of light. So the wavelength has to be in meters for this to cancel. 900 nanometers, we're going to have to convert that to meters. So in every 1 meter, there are 10 to the 9th nanometers. So let's just go to our calculators. 900 divided by 10 to the 9th is 9 times 10 to the minus 7th. 9, I'm just going to put 9.00 times 10 to the minus 7th. Meters. Meters will cancel. And when I put this into my calculator, 3 times 10 to the 8th. Now, be careful how you enter this. Make sure you enter it correctly. Just make sure if you have scientific notations that you're putting parentheses around the scientific notation, like the whole value. So divided by 9 times 10 to the negative 7th. Whoops. And you will get 3.33 times 10 to the 14th s to the minus 1. S to the minus 1 because S is the surviving unit, but it's in a denominator, and that is the correct unit for frequency. That's the number we're going to implant in here. 3.33 times 10 to the 14th s to the minus 1. You'll see that s to the minus 1 will cancel out s because that's in a numerator, that's in a denominator, and they'll cancel. And then you'll be left with joules, which makes sense. You're looking for energy of a photon. So now just take that number, which is hopefully still in your calculator, and just times it by Planck's constant. And I'm getting 2.21. Now, I kind of messed with you with the Sig Figs. I know this is ambiguous, but I'll be more careful with that on the test to make sure it's not ambiguous. But let's just pick two Sig Figs. 2.21 times 10 to the negative 19th joules. And that would be the answer for the first part of this, the energy of the photon of this light. If visible light is between 400 and 750 nanometers, which it is, so visible light is between, so this is getting into the electromagnetic spectrum. Remember, the electromagnetic spectrum, just as a quick review, was radio, microwave, infrared, visible, UV, X-ray, gamma radiation. These are all the different types of electromagnetic radiation. With gamma, with this side of the electromagnetic spectrum being the high energy, high frequency, but short wavelengths. Okay, and then this side being the low energy, low frequency, long wavelength, or large wavelength. Okay, so if it's saying that visible light is between 400 and 750, so essentially the shorter wavelengths I'm writing to the right. So the 400 would have to go somewhere like here, and the 750 would go here. If you think about it, the wavelengths are getting longer as you move to the left, according to this representation of the electromagnetic spectrum. This energy of the photon is 900 nanometers, so it's a little bit longer than where visible ends, and so the answer there is infrared. It's just getting you to kind of remember the electromagnetic spectrum and like especially the relationships of frequency, wavelength, and energy. And that is how you do question number 2. Moving on to question number 3. Consider this reaction. So I'm just going to go ahead and write that reaction on the board. 2 magnesium solid plus O2 gas yields 2 MgO, 2 magnesium oxide, and I actually don't have a phase label there, but it probably was solid. delta H is equal to negative 1204 kilojoules. And you really, that's a typo. It really should have had a phase label. Anytime you attach the delta H to the right of an equation and turn it into what we call a thermochemical equation, you absolutely have to have phase labels. That's a requirement. All right, so I got that on the board. Now, A, is this reaction exothermic or endothermic? If the delta H is negative, it's exothermic. That means it's releasing heat into the surroundings, and it would feel hot to your touch. So that's easy. Letter B, how many grams of magnesium would be required to produce 556 joules of heat according to this reaction? Alrighty, so you can see in part B, the only number in the question is 556 joules. So that's the number you always start with. If there's only one number in the question, that's what you would write to the far left. And the key here is that you can, we're trying to solve for grams of magnesium, okay? So we're trying to solve for grams of magnesium, and we're given the amount of heat. The key is when you're given a thermochemical equation, you can relate the amount of heat to any amount of species. And it looks like you just write a conversion factor. So I'm going to relate this amount of heat to this species because this is the one that the question is about. And so I want the joules to be on the bottom. You just write it as a conversion factor. And essentially you're saying, I will produce 1,204 kilojoules. I'm kind of losing the negative because the negative is just telling me that it's leaving and not coming in, okay? But this is the amount of heat that you'll produce. 1,204 kilojoules per, that's the fraction line, per 2 moles of magnesium. That is the relationship. In the thermochemical equation, these refer to the amount of moles of each species. So you can write these conversion factors relating the heat to the number of moles, almost like stoichiometry. Oh, I see a little problem. Joules won't cancel kilojoules. So I needed to convert joules to kilojoules first. 556 joules I should have had in every 1,000 joules is 1 kilojoule first. Now kilojoules will cancel. And then now I'm in moles, and all I need is to turn that into grams. That's just the molar mass. And magnesium, 24.31 grams per mole. And that should get me the answer. 556 divided by 1,000 times 2 divided by 1,204 times 24.31. And the answer that I'm getting is 0.0. Let's go to the Sig Figs. That has 3 Sig Figs. This one has 4, so I'll pick 3. 0.02245, but the 5 would bump the 4 up to a 5, so that should be the right number of Sig Figs, and the surviving unit being grams. And that would be the right answer. So this is relating stoichiometry to heat produced. And that is a topic from from the thermochemistry chapter, chapter 6, probably in the second video. Alrighty, moving along to question number 4. Question number 4. If 10.00 kilograms of liquid water, so 10.00 kilograms, liquid water is a little bit of a, you don't really need to say liquid water. Water is always a liquid. I don't know why I wrote that, but anyhow. At 24.6 degrees C, absorbs 904 kilojoules of heat. What will its final temperature be? So this time I have an initial temperature. It's 24.6 degrees C. That's what it was at the beginning. I can read in the question that it is absorbing 904 kilojoules of heat. So I can tell that Q, the amount of heat, is actually a positive number. It's absorbing 904 kilojoules of heat. If the heat was being released from the water, which is another, possibility, then you would have to do a negative right there. So it actually does really matter. You have to make sure you read, just like earlier with delta E equals Q plus W, you have to read the question to make sure if it's absorbing heat or warming up, then it's a positive Q. If it's releasing heat or cooling down, then it would be a negative Q. What will its final temperature be? So I'm trying to solve for T final. So anytime you have a change in temperature, some kind of a change in temperature, and you're trying to relate it to the amount of heat that either came in or out, that is the very famous equation, Q equals M times specific heat capacity times delta T. That's the appropriate equation to use, okay? This is not a thermal energy transfer question. This is literally, you have one substance. You don't have two different substances you're discussing. It's just one substance. It absorbs some heat. What's the new temperature? So it's actually a fairly simple equation. So, however, this time we're trying to solve for T final. What I would do, anytime you're asked to solve for either T initial or T final, I would just fixate on solving for delta T first. Okay, just kind of turn this into a two-step problem. I think it's easier. I think most people will make fewer mistakes. So let's solve for delta T first. Let's just go ahead and rearrange this equation for delta T. So delta T is equal to Q over mass times specific heat capacity. Keep in mind that the units all have to be correct. So let's start with the specific heat capacity. Let's put that in first. So specific heat capacity is 4.18 joules over gram degree C. That's and this specific heat capacity, I would never try to change the units. Change the other guys to match his units. Like think of his units as the correct ones and make the other M and Q match his units. That's a little bit, I think it makes more sense. So mass is going to have to be in grams so that it cancels. You can see that it's in kilograms. So let's go ahead and convert kilograms to grams. And every 1 kilogram, there's 1,000 grams. So we're literally just timesing by 1,000. So 10 becomes 10,000 grams. So grams will now cancel. And the Q is going to have to be in joules. And it's in kilojoules. So same thing, we're going to have to make this match. In every 1 kilojoule, there are 1,000 joules. And so this time, this becomes 904,000 joules. Alrighty. So now, and that will cancel out joules. And you can see that your surviving unit will be degrees C, which makes sense because we're solving for delta T. So let's go ahead and figure out what this is. So I'm going to go ahead and do 904,000 divided by, now anytime you have like a multiplication in your denominator, it's essential that you do 904,000 divided by, but you got to make sure you do your parentheses. And that in the bottom, you're doing 10,000 times 4.18. And then close the parentheses. And I'm getting that delta T is equal to 21.663 degrees C. Okay, that's delta T. Now be careful, that's not exactly what the question asked for. The question wanted T final. So from delta T is always T final minus T initial. So if you're trying to solve for T final, you would add T initial to both sides. And that would give you T final. So to get T final, we need to do delta T, which is this number here, and we're going to add T initial. We're going to add 24.6. And I'm getting, for T final, for my, my answer, 46.2 degrees C. And now, as a last check that you did it right, make sure that the temperature went the right way. You had a sample of water. It absorbed heat. It should have gotten hotter. Did it get hotter? Indeed, it did. Okay, so, and usually the questions, when I write questions or when a book writes questions, they try to make them reasonable. If you got an answer like, you know, 5,750 degrees C or something for T final. That's not really a reasonable question. The water would not get that hot. It would have turned into steam. So make sure you kind of think about whether the answer is reasonable. That will help with these types of questions, because if you forgot, say, one of the unit conversions or whatever, then your number could have gotten really crazy. So it's kind of just a smart way to evaluate your answers, and that's something you should be doing. All right, let's go ahead and move on. To question number 5. Calculate the standard enthalpy change for the following reaction using standard enthalpies of formations. All right, so this topic was covered in its very own video, standard enthalpies of formations. If you skipped that video, you want to go back and watch it. That content is on the exam, and there's stuff in there that's even beyond what I'm putting on the board here. So you want to make sure you watch that video. Okay. So we're trying to calculate the standard enthalpy change for this reaction. Enthalpy change is delta H. Standard enthalpy change literally just means that you have this little circle here. It just means that under standard conditions, it's not a huge thing that you need to worry about, but we're trying to figure out that delta H. There are several different ways to find out delta H. One of them is to use Hess's law, which is like that, where you've got the steps and you add them up and all that. Another way is to conduct an experiment, to do calorimetry. That was one of our labs was supposed to be in that this year, but we were out of school. And then another way is standard enthalpy of formation. So that's this way. So to use standard enthalpies of formations, essentially what you want to recall is this main equation. To get your standard enthalpy change for a reaction, you want to add up or get the sum of all the standard enthalpies of formations of the products. And you want to subtract the sum of all the standard enthalpies of formations of the reactants. It's always the products minus the reactants, which should make sense because anytime you have a delta, it's always the final, which is the products, minus the reactants, or the initial, which is the reactants. So that is consistent. Now, we need to look up those standard enthalpies of formations, and they are, I guess I probably should have put them on here. They are in your textbook, which for me is in the other room. So I got to go run and get my textbook so I can look at these numbers. I'll be right back. All right, on the exam, you will have a question similar to this. I will just give you these so you don't have to look it up. I know some people are using like online textbooks or whatever, so it's a little bit challenging. But anyhow, if you have your textbook, Appendix 2 has all the standard enthalpies of formations. So let's start with this one. You just have to look for, you have to find this compound underneath the appropriate element. So usually it's under like the most unusual element or something. So magnesium. So look under magnesium, and you should be able to find MgOH2 solid. Now make sure you grab the correct phase. The appendix looks like this. And I can see MgOH2 solid, magnesium hydroxide. The delta H of formation is negative 924.5. I'm just going to write that underneath it. Negative 924.5. Now it has a unit. It's kilojoules per mole. All right, so let's grab that one. Then look up the other. So MgO solid, he's right above. He's negative 601.6 kilojoules per mole. And water is actually under oxygen. Now you got to make sure you pick the correct form. H2O liquid has a different standard enthalpy of formation than H2O gas. So make sure you pick the right one. So liquid is negative 285.8 kilojoules per mole. So you want to gather your standard enthalpies of formations, and I literally just write them underneath. Okay, now the key here, and I don't have any coefficients on this equation. I probably should have as a better practice question, but if you have coefficients, so this stands for 1, everybody knows that. Okay, you want to multiply the standard enthalpies of formations by the number of moles. So you have 1 mole of this. So you can see that this number is not going to change. So if you had forgotten to do it, it wouldn't have affected your answer. However, if this had been a 2 and you forgot to do it, it would, you'd get the wrong answer. So as a matter of habit, even if it's a 1, times it by 1 mole, and frankly, that's where the mole unit goes. So we have 1 mole of this, we have 1 mole of this, and we have 1 mole of this. Okay, and now we can gather our sums. So I usually just do I divide the reactants from the products. So let's get the sum of all the products. Let's do that one first. So this coefficient doesn't change the number. If it had, you would have had to do that out and find out how much heat equals. So we have negative 601.6, and we're getting sums. We're adding. We're going to add this number plus negative 285.8, and that gets us negative 887.4 as the kilojoules as the sum of the products. And then let's get the sum of the reactants. Well, there's nothing to add here, so it's just this, negative 924.5 kilojoules. So you get your 2 sums, and then to get the final answer, you take the sum of the products and you subtract the sum of the reactants. So we're going to do negative 887.4, and we're going to minus negative 924.5. And I'm getting an answer of 37.1 kilojoules. And that is the answer. Where people usually mess up a problem like this is they forget to include the coefficients, which, like I said, this one didn't affect your numbers. But if you had 2s, 3s, or 4s, or whatever, it would have changed it. You would have had to multiply it to get a bigger number. And then secondly, a lot of times people just kind of get sloppy with the signs. Make sure that you do the signs correctly in your math. And that should be the answer. So that would be an endothermic reaction absorbing 37.1 kilojoules every time you get a mole of that reacting. Alrighty, moving on to the next question. Question number 6. Complete combustion of acetic acid releases 871.7 kilojoules of heat per mole of acid. Write a balanced thermochemical equation. Okay, a balanced thermochemical equation is just going to be the balanced chemical equation with the delta H written to the right and making sure that you have phase labels. So we need to write, let's start by just getting a balanced chemical equation. Combustion of acetic acid. Well, should know by now the formula for acetic acid, HC2H3O2. We should also know the phase label is aqueous. If it's an acid, you write aqueous. Combustion means that you are burning it in the presence of O2 gas, and your O is making the same 2 products, CO2 gas and H2O gas. All right, and we are going to make this a thermochemical equation. But before we do that, record that number. Let's make sure we balance this. All right, so we only have H, C's, and O's. So we, how I usually do it is I usually balance the C first, then the H, and then the O last. The O is a good thing to balance last because you can just make this any number that you want and kind of fix it. So let's look at C's first. So there's 2 carbons in acetic acid. I only have 1 here, so let's go ahead and fix this. And I don't even know the answer right now. And so you can see it's just trial and error. So 2 carbons. Be careful with hydrogens. Make sure you add all of them. So there's 3 here, but there's another one there. So I have 4 hydrogens on the left side, and I can get 4 by adding a 2 right here. And now let's see what the oxygens look like. I'll start at my right side here. I've got 4 oxygens right here, plus 2 more there. So that's a 6 total oxygens. I've got 2 here, so I need 4 more, and I can get that by doing a 2 right there. So that will give me a balanced chemical equation. Thermochemical equation just means make sure you have your phase labels written in, and then just record the amount of heat. Now, it says that the combustion releases 871.7 kilojoules per mole of acid. So for every 1 mole of acid, you get a delta H of negative 871.7 kilojoules. Now, why did I choose a negative number even though it wasn't written in here? Because of the wording. It said that it released heat. It's telling me that this is an exothermic reaction, which, by the way, all combustion reactions release heat. You know, anything you've ever burned, hopefully you felt heat's coming out of that thing, and it's true for any combustion reaction. And that is the amount of heat you would get from a mole of acetic acid burning. Now, draw an enthalpy diagram for the reaction. Enthalpy is capital H. So an enthalpy diagram will look like this. H on the y-axis. Sometimes I've taught you energy diagrams as well, but enthalpy diagram would be H, not E. And on the bottom, it's always the same, reaction progress. At least that's the wording that I prefer. Some people like reaction coordinate, but I use reaction progress. Now, if you have an exothermic reaction, that essentially means that your products, because remember, delta H, another way of thinking about delta H is that it's the enthalpy of the products minus the enthalpy of the reactants, final minus initial. So the only way that you're getting a negative number, okay, just think logically about this, is if this number is a smaller number than this number. Okay, the only way to get a negative number from a subtraction is if you do small minus large, like 5 minus 10 or, 1 minus 3 or something. So small minus large. So the enthalpy of the products needs to be lower than the enthalpy of reactants for a exothermic reaction. For an endothermic reaction, it would be reversed. This is what endothermic reaction would look like. But exothermic looks like that. And so all you have to do is just record the 2 products, the 2 reactants. I'll just do it like this. Draw them higher than the reactant, or draw an arrow like that, than the products. Okay, and that's what the enthalpy diagram looks like. Now, to make it kind of complete, what most people would do is kind of note the fact that the difference between this value and this value, the H of the reactants and the H of the products, would be the delta H. And in this case, it would be negative 871.7 kilojoules. So that is an exothermic reaction. Essentially, that just means the heat is flowing out into the surroundings. The heat that you're losing, so to speak, or the heat that you used to have in your species that you don't have anymore has left. Okay, that's what exothermic means. And that's an enthalpy diagram. That was in the second thermochemistry video. Question number 7. Okay, how many unpaired electrons are in an arsenic atom? Which orbital sublevel are they in? Identify the 4 quantum numbers of the very last electron in arsenic's orbital diagram. So this is chapter 7 and 8 topics, and it looks like all the rest of these are like chapter 7 and 8. The exam, I've written it, is very much spread out between 6, 7, and 8. And as I was writing it, I was remembering my videos. So if you didn't watch any one video, and you get a question on the test and you're like, I don't know how to do this, because this is not all that's on the test. This is just helpful. It will springboard you. Trust me, it will be useful, but it's not everything. You have to make sure you're watching those videos. So if there was one that you never got to, watch it. Even Even after you get the test, watch it and it should help you. Okay, arsenic, AS. So anytime you're asked about like unpaired electrons or whatever, you should be thinking about orbital diagrams, because the orbital diagrams are the place where you can see the unpaired electrons. But before you do an orbital diagram, usually I do, at least I do, a electron configuration. So arsenic, let's go ahead and do arsenic's electron configuration. Arsenic is atomic number 33, so that means it has 33 electrons. And you can either use the diagonal rule and start filling up the orbital sublevels until you run out of electrons, or you can read your periodic table. You should get the same answer either way. So let's start with an electron configuration. Even if it didn't ask you for it, it is helpful to write that first. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then 4p3. Now, one of the things that I did not cover in my videos was the noble gas abbreviation. Part of the reason why I didn't cover it is because I don't want you to use it. The noble gas, I'll just mention it here. The noble gas abbreviation is basically starting, you find the noble gas that comes before it. So arsenic, the noble gas that you reach before him is argon. And you can put that in brackets, and that basically says, okay, including all the electron configuration of argon, just continue on from there. So argon, and then you would just continue on with 4s2, 3d10, 4p3. You can see that the ending is still the same, and argon's electron configuration accounts for the rest of it. It's like a shortcut method. I don't really, I will write on the exam that I don't want you to use that, but I'll just mention it right here. I want you to kind of prove that you can, write a whole electron configuration. Anyhow, how many unpaired electrons are in an arsenic atom, and which orbital sublevel are they in? Okay, so from the electron configuration, you can write an orbital diagram. Now, I'm just going to do the whole thing because you don't really have to do the whole thing for this question. If you are pretty good at this, you can see it's a pretty easy answer. But let's just do it just in case some people are still feeling unsure of this. The 1s has 2 electrons in it, spin up, spin down, because of the Pauli exclusion principle. Same with the 2s. The 2p6, fill up singly before you double up. Singly with parallel spins before you double up. 3s. I'm just turning this electron configuration into an orbital diagram. 3p6. So all of these guys are full. Now, 4s2, spin up, spin down. 3d10. That's 5 boxes. This is all full, but they did fill up singly before we doubled them up. Okay, that's the 3d10, and now we're at the end here. So now you really could have just actually jumped to this part, because knowing that all of these numbers are full, like 2 is the maximum, 6 is the maximum, 10 is the maximum, you really could have just zeroed in right here for the answer. 4p3, so this is the 4p sublevel. You have 3 electrons. The key here is you remember Hund's rule demands that they fill up singly with parallel spins before they double up the electrons. So the answer to this is that arsenic has 3 unpaired electrons. That's the first answer. Which orbital sublevel are they in? They are in the 4p sublevel. Remember, a sublevel is just basically like a set where they all have the same N and L. So this is the 3D sublevel. It includes all 5 orientations. This is the 4p sublevel. It includes all 3 orientations. And then the last thing is identify the 4 quantum numbers. So that's N, L, ML, and MS of the very last electron. Okay, so we need the 4 quantum numbers of him, the very last electron. I mean, I could have asked really any electron, but for the sake of kind of clarity, I'm asking about this one. So let's go through the N, the L, So what's the N, what's the L, what's the ML, and what's the MS? Okay, the N value is the integer of the orbital. So this electron is in a 4p orbital, so therefore the N value is 4. The L value is referring to the shape. Now, it's a number though, it's not a letter. What you have to remember is that when we went over the quantum numbers, the L values are 0, 1, 2, and 3. And the shapes that those correspond to are S, P, D, and F. So if you have a P orbital, that L value is 1. Okay, so that's the L value, 1. Now, the ML values, remember when ML can be all the integers from negative L to positive L. So if L is equal to 1, that means that ML can be all the numbers from negative 1 all the way to positive 1 on your number line. And you would just label these in order. So negative 1, 0, positive 1, like left to right on your number line. So the ML value for this one is positive 1. And the MS value, if it's spinning up, would be plus 1/2. And that is how you would identify the 4 quantum numbers for any one electron. Alrighty, moving on to question number 8. And all of that quantum number stuff was at the end of the chapter 7 video and kind of like the beginning of the chapter 8 video, kind of spread out between both. Question number 8. If an electron transitions, okay, we're talking about electron transitions, moving. What you immediately want to think of is the Bohr model. And the Bohr model is this whole nucleus down here. And you've got these N levels. N equals 1, N equals 2. And in the video, I made that point that the levels do get closer and closer together as they move farther and farther away. So I just kind of recreated a little Bohr model. So we have an electron transitioning from 1 to 4. Okay, so he's going from 1 to 4. Now, once again, it's not like a traveling, it's like an instantaneous transition. If an electron goes from 1 to 4, will that be accompanied by the absorption or the emission of a photon? Anytime the electron is jumping up to a higher energy level, it's just like any other energy. Like, I mean, what takes more energy, to jump up in the air or to just fall back down? Certainly you feel it. I mean, it's a lot harder to jump in the air than to fall back down. It takes a lot more energy to walk up a hill than down a hill. I mean, many different ways to think about it. But if an electron is trying to jump, that is going to require the absorption of a photon. A photon is going to have to come into that atom and essentially give that energy, or give that electron the energy to jump up. In contrast, when an electron falls back down, that's the emission of a photon. Okay, but absorption of a photon to push him uphill. That's the first part. What will the wavelength of that photon be? All right, so anytime you have a question about an energy transition, so this time we're going from N equals 1 to N equals 4. That's the transition that we're discussing here. There's an equation that governs this. The energy of the photon that is either absorbed or released. This time it's going to be an absorption, but the energy of the photon is equal to negative 2.18 times 10 to the negative 18th joules. This is the equation that governs electron transitions, times 1 over N final squared minus 1 over N initial squared. If you Google this equation, sometimes it's presented with a positive number here, but with these two switched, which will give you the same answer. But don't do that. Just stick with the equation that I'm giving you. It's the same one that your book uses. But I'm just telling you, just in case you're seeing it somewhere else and you're like, hey, she got it wrong or whatever, you'll notice if it's positive there, they switch the initial and the final, which would end up giving you the same number. All right, so let's just get the energy of the photon. This is pretty simple. We have the two ends, and we have this number. So it's all you really need is the initial and final. Now make sure you do it right. This is the initial. That's N initial. That's N final. So make sure you read it correctly here. So I usually do this part first. So 1 over N final squared. So what's N final? It's 4. 4 squared is 16. So I'm going to do 1 divided by 16. Okay? And from that, I'm going to subtract 1 divided by 1 squared, which is just 1. So I'm going to subtract 1. And that ends up being negative 0.9375. And I'm timesing that by this number here, negative 2.18. I'm putting this in parentheses, the whole thing. Negative 2.18 times 10 to the negative 18th. And I'm getting 2.0438. I'm not going to round too much because I'm not really done yet. Times 10 to the negative 18th joules as an answer. Now notice, the energy of the photon is positive here. That's consistent with the fact that the photon came in. If you had a transition from like a low to a high to low, you would get a negative number for this photon, which means essentially that the photon is coming out. So it's the sign that you end up with is consistent with whether you're having absorption or a release. Now, that's the energy of a photon, but that's not really what, I mean, I'm on my way to the answer. I wanted the wavelength of the photon. So to get wavelength, we have to really understand that the only equation that I'm giving you with wavelength is this one. Okay, so which is essentially useful for any time, for understanding that anytime you have frequency, you can get wavelength, and vice versa. So I can't get it immediately, but I'm going to be able to get frequency because the energy of a photon, so 2.0438 times 10 to the negative 18th joules. And another equation, let me go ahead and write this down here. Another equation for energy of a photon is H times frequency, Planck's constant times frequency. So let me get a better marker. So if I've now calculated my energy of my photon. Now I can get frequency by setting it equal to Planck's constant, 6.626 times 10 to the negative 34th, joules times seconds, times frequency. So I will get frequency if I divide both sides by H. And I've still got this in my calculator, so I'm just going to divide by Planck's constant. 6.626 times 10 to the negative 34th. I'm getting a frequency equal to 3.084 times 10 to the 15th, s to the minus 1. You can see that the joule unit's going to cancel. And now I can take that frequency and bring it to this equation to get wavelength. So getting quite close. And this is oftentimes a stepwise, series of equations that you need to solve with these types of questions here. So to get wavelength, I would divide C by frequency. C is the speed of light, and it's in meters per second, so frequency is in the correct unit. Let's see here. Speed of light, 3 times 10 to the 8th, divided by what I have in my calculator for frequency. And for wavelength, let me put it up here. I am getting 9.7 times 10 to the negative 8th. It's really 9.7. Let me have one more sig fig here. 9.73 times 10 to the negative 8th. Now, the unit would be meters because speed of light was 3 times 10 to the 8th meters per second. So the length unit that you get for wavelength would be in meters. Anytime it's kind of really a tiny amount of meters, it makes more sense to present it as a micrometer, nanometer, picometer, whatever one puts you in a kind of a reasonable ballpark. Let's choose nanometers here. I would have accepted this for an answer, by the way, because that is the right answer. But I think on Answer key, I put it in nanometers. So in every 1 meter, there's 10 to the 9th nanometers. So times that by 10 to the 9th, and you will get the right answer. I'm getting 97. 97.3 nanometers. 97.3 nanometers. And I'm not sure, Sig Figs, I'll probably be a little bit relaxed about that. Let's see here, because here, well, n equals 1 and n equals 4, those aren't really measurements. Those are kind of exact numbers. So yeah, I think the answer actually should be 3 Sig Figs based on this number here. But I'm not sure what I have in the answer key. But anyhow, 97.3 nanometers would be the perfect answer. All right, we are on to the last problem. But like I said, I would have accepted that number as well. Unless I specifically asked for it in nanometers, I suppose I could do that. But if I just asked for wavelength, you really can give it to me in any meter type of unit, as long as it's an SI unit. All right, question 9, almost done. Last question. What are the 4 different quantum numbers? Include their names, abbreviations, what they describe about the orbitals or electrons, and what are their possible values. Okay, that's all from the last chapter 7 video, and I'm not going to re-teach it here. So you can go ahead and look at that video. So I'm looking for NL, etc., principal quantum number, angular momentum quantum number, and then what they tell you about the orbitals or the electrons. And the last quantum number, the MS, that's in the chapter 8 video, the first chapter 8 video, because that one is taught kind of after you learn about electron configurations. All right, which of these combinations of quantum numbers are possible and which are impossible? Let me go ahead and jot these on the board. 2, 2, negative 1 plus 1/2. 1, 0, 0, minus 1/2. 4, 1, negative 2 plus 1/2. And 3, 2, 0, and 0. Okay, this has everything to do with the concept of possible values. Once again, at the end of the chapter 7 lecture, the quantum numbers have only certain possible values according to Schrodinger's mathematical probability equations. And so you have to kind of apply those rules and see if these combos are possible. Let's start with the first one. And these are all in the traditional order, N, L, ML, MS. Okay, 2. Can n equal 2? The answer is yes. N can be any number from 1, as long as it's a positive whole number. So 1, 2, 3, etc. N cannot be 0. So if you have an n that equals 0, it's immediately impossible, because that can't be. Anyhow, back to this one. When n equals 2, what are the possible values of L? So L can be all numbers from 0 to n minus 1. So when n equals 2, L can only be 0 and 1. So this is immediately impossible, because L cannot be 2 when n equals 2. So let's move on to the next one. N equals 1, that's fine. When n equals 1, can L be a 0? The answer is yes. L can be all numbers from 0 to n minus 1. So, in fact, that's the only number that L can be when n equals 1. Let's look at the next one, ML. Can ML be a 0 when L is 0? Yes, it can be. And then the MS value, negative 1/2. As long as this is either plus 1/2 or minus 1/2, it's fine. So this one is possible. Let's do this one here. N equals 4. That's fine. N can be 4. Can L be 1 when n equals 4? Yes, it can be, because L can be all numbers from 0 to n minus 1. So if n is 4, L could be 0, 1, 2, or 3. All of those would have been fine. But in this case, we have a 1. Now, when n equals 1, when L equals 1, can ML equal negative 2? No. When L is 1, ML can only be negative 1, 0, or positive 1, not negative 2. So this one is impossible. Understand that the ML value is dependent on L, just like the L is dependent on N. This last one, n equals 3, that's fine. If n equals 3, can L equal 2? The answer is yes. If L equals 2, can ML equal 0? The answer is yes, because if L equals 2, ML can be negative 2, negative 1, 0, positive 1, or positive 2. So it can be a 0. That's fine. However, can MS be 0? And the answer is no. MS has to be +1/2 or -1/2. And that's how you tell if a certain combination of quantum numbers is possible or impossible. So I would expect some questions like that in the test. All right, hopefully that was helpful. Feel free to ignore it if you didn't need it, or just jump to, whatever question is good. But good luck studying, and hopefully everything goes good for you.